Hi, my name is Justin, and today I'm going to talk a little bit about how dimensional analysis was used to develop the experiment for the Granular Flow Lab. So, to begin with, we will look at the basic premise that we want to study. So we have some vertical column we're going to be filling up with material, and we're going to be allowing that to flow out of some orifice. And they can have different shapes. You can have squares, you could have circles, you could have triangles, you could have any shape really. So to use dimensional analysis to come up with an experiment where we can find out what different parameters in this system affect the mass flow rate of these granular particles the most. So to begin with, we're going to list all of the different parameters that can affect the mass flow rate in this system. So the first thing will of course be the mass flow rate, because that's what we're looking for. So we'd also maybe consider the height that we're packing the material into this, the diameter of the column that we're filling, the hydraulic diameter of the orifice, the individual size of the particles, which we're going to be assuming are spherical, their bulk density, their true density, the gravity force, that'll be the main force causing the flow, and then there'll be some shape factor that will affect it. So we can write all of these out. So we've got mass flow rate, we've got hydraulic diameter, and it's important to note with hydraulic diameter that that is 4 times the area over the perimeter. So it's taking in somewhat the shape of that orifice. So we've got the packing height, or the head if you want to think about it in terms of fluids. We've got spherical diameter of the particles. We've got density, we've got bulk density, we've got diameter of the vessel, we've got gravity, and we've got some shape factor. So we've listed, these are all the parameters we're going to consider. So there are definitely parameters that we're leaving out here. We aren't considering friction between the particles and the edges of this column. We aren't considering friction between the particles and each other. We aren't taking any temperature effects into account. We aren't considering static forces. So that can be a big deal, especially so in the case we're going to be using plastic beads, and plastic beads can build up a lot of static electricity. So we're not considering air pressure or humidity or any of stuff like that. So there are parameters we're leaving out of this, so we're neglecting to account for some things. So we've listed all the parameters we're going to consider. Now the next step is we need to list all of these parameters in terms of their dimensions. So not just their units, because we don't want to assign units to anything right now. We want to think about what are the dimensions of each of these. So mass flow rate is mass per time unit. Hydraulic diameter is a diameter. Packing height is a length. Packing height is a length. Spherical diameter is a length. Density is a mass per length cubed. So is bulk density. Diameter is a length. Gravity is length per time squared. And our shape factor doesn't have any dimensions. So now that we've listed all the properties in terms of their dimensions, we can decide what the primary dimensions are. So the primary dimensions are however many dimensions are needed to represent all of the parameters that we're going to consider. So for the parameters that were chosen, the ones that we're going to use in this dimensional analysis, we would need mass, length, and time to represent all of these. So next we're going to go through our parameters, and we need to choose some repeating parameters. So repeating parameters are things that we can measure easily. They're things that we're going to keep constant throughout the experiment, and they want to be stuff that we can control. So these repeating parameters are going to be used to make our dimensionless groups. They're going to end up in every dimensionless group. So error in the repeating parameters will show up everywhere. So that's why we want to make sure they're things we can control, things that we can measure. And they want to be constant because they're things that we cannot change because they're part of every dimensionless group. So for our experiment, we're going to make some assumptions about what will affect the mass flow rate the most, and some assumptions about our material. So we're going to use bulk density, spherical diameter, and gravity as our repeating parameters. So we're saying our material packs together in the same way every time. We're saying all the particles are the same size, and we're saying that gravity doesn't change. So this is probably a fairly safe assumption. Gravity is going to be constant. Our tube isn't miles high. We aren't doing the experiment in lots of different places. Gravity is going to be the same during our experiment. Now, whether the spherical diameter and the bulk density are constant, those may or may not be true. So bulk density can change based on how the particles pack together. So if they pack together differently different times, then the bulk density will change. If the particles aren't all the same size, then bulk density almost certainly won't be a constant, because different particles will pack together differently if they're different sizes. So these are possible sources of error. So when we write out all of these parameters, what we're saying is our mass flow rate is some function of the rest of these things. So we're saying that our mass flow rate is some function of all these parameters that we're considering. So now we can make, using our repeating parameters, some dimensionless groups. So that will allow us to have different, we'll call them pi groups, that don't have any dimensions in them. And that allows us to scale our experiment to some set scale. And then we can interpolate from that at different scales if we needed to. So coming up with dimensionless groups. So our first dimensionless group is going to be our dimensionless mass flow rate. And that is going to be our pi 1. So we come up with dimensionless groups by taking the parameter we're going to be making a dimensionless group for, and multiplying it by our 3 repeating parameters taken to arbitrary exponents. So this allows us Now to find A, B, and C such that we end up with m to the 0, L to the 0, T to the 0. So we have a dimensionless group in here. So to do that, we're going to write each of these parameters in terms of their dimensions. So our mass flow rate is mass over time. Our bulk density is mass per length cubed. And again, that's brought to an arbitrary exponent A. Our particle diameter is just L. That's brought to arbitrary exponent B. And gravity is length per time squared. And that's to arbitrary exponent C. So we've got 3 dimensions that we want to get rid of. So we can write 3 simultaneous equations, and then we can solve for A, B, and C. And if we do it correctly, we'll end up with a dimensionless group that has no dimension to it. So for M, we've got 1 plus A, and then there's no mass in that term and no mass in that term. And we want that to equal 0. So from that we can see that A must be -1. We can do another equation for L. So we have minus 3A plus B plus C. So there was no length term in that, and then there was length terms in those 3. And we want that to equal 0. Now we can't solve this one yet because we have 2 unknowns. So let's go on to our third equation for time. So we have -1, and then no time in either A or B term, and then minus 2C. And we want that to equal 0. So from here, we can see that C is -1/2. Now, if we plug in A and C into this equation, we get that B must be -5/2. So now we put all these back into here, and we have our first dimensionless group. So that is our dimensionless mass flow rate. So following this same idea, where we would take the parameter we want to make a dimensionless group for, and then we will multiply it by our 3 repeating parameters brought to arbitrary exponents, we can find the rest of our pi groups. So pi group 2 is going to be our dimensionless packing height, and that will end up being h over the spherical diameter. Pi 3 will be the dimensionless hydraulic diameter, and that will be dh over ds. Pi 4 will be our dimensionless column or tube diameter, and that will be d over ds. Pi 5 will be our dimensionless true density, so the density of the actual particles, and that will be rho over rho b. And pi 6 will just be a dimensionless shape factor, because it was already dimensionless. So now we've gone from saying that our mass flow rate was a function of all these parameters, and now we can say pi 1 is a function of these dimensionless groups. So we're a little bit closer to having an experiment. So again, we've got these different dimensionless groups that we're saying affect our mass flow rate. So we've already made some assumptions. We have said that all the particles are the same size and they always pack together the same way. So if they're all the same size, they're all made out of one material, they always pack together the same way, we've already assumed that this is a constant, essentially. So then of our other four parameters here that we're looking at, we've got dimensionless packing height, dimensionless hydraulic diameter of the orifice, so how large of an orifice are we flowing out of, dimensionless diameter of the column, and dimensionless shape. So the hydraulic diameter of the orifice already accounts somewhat for the shape. So we will use just one shape. So we can say that that's a constant. And then of these, it's probably most likely that height that we pack the material into and the size of the orifice that the particles flow out of are going to be more important than the diameter of the column, because the packing height will add pressure to the particles flowing out of the bottom, just like it would for increasing the height of a water column, and allowing a larger orifice for it to flow out of will provide less resistance for those particles to flow out of the column. So we will also use just one tube diameter. So now we can say that our dimensionless mass flow rate is a function of some constant, that is these three parameters combined, our dimensionless packing height, and our dimensionless orifice diameter. So this is something that we can use to develop an experiment. So we've got one parameter we're looking at, and we've got two parameters that we want to see how they affect this. So to do this, we're going to assume a power function for this f. We're going to say that this function is a power function. And by doing that, we get this equation. So we've raised these to arbitrary powers that we're going to call N2 and N3. So now we can use this function to develop an experiment to find out whether the packing height or the orifice diameter has more of an effect on the mass flow rate of our materials. So that is why we do two experiments for this granular flow lab. So we do one experiment where we fill the tube up to the same height every time and vary the orifice diameter. And then we do another experiment where we keep the orifice diameter constant and we vary the height. And by doing two plots for those two experiments, we can use a power fit to find N2 and N3. And then that will also give us some constants we can combine to get this C. So the point of the experiments is to find values for C, N2, and N3. And then those values will allow us to determine how the packing height and the orifice diameter affect the mass flow rate. So that's all I have to talk about for this lab. Thank you, and if you have any questions, email one of the TAs for the class.